All right, so we talked about some of the basics of kind of simple linear regression. Some other things that we might start wanting to know about when we start to compare relationships is going to be something called the R squared. So I don't know why I said of course, but it means the coefficient of determination. Basically, it's the amount of variation or the percent of the variation that we can explain um, in the y variable. So the amount of variation in the dependent variable that's explained by our x variable or explained by our regression. Now, eventually we'll say, it's explained by not just one x variable, we can include several, but for now, just one is where we're at. So there's going to be something called the sum of the squared residuals and the total sum of squares, right? So we can kind of think about what this is telling us. So here I'm looking at what are the deviations of my predictions from the average y value, right? So this is kind of like how much variation would exist in the data if the only thing that was going into y was the different x values and my slope and intercept coefficient. This doesn't include the error term, right? So this would be the variation that I can explain using my predictions. Now the total sum of squares is going to be all the variation that exists in those y variables, right? So here, because I know that y is always going to be different than my predicted y, because it's always going to include some error term, right? I'm only going to be able to explain a certain amount of variation, excuse me, with my predictions. The ratio of the two then tells me, okay, and I said tells me the percent of variation. Technically, the R squared, the way it's going to be displayed, it's going to be in decimal form. So it's the proportion of the variation we can explain. And we then often multiply it by 100. And when we talk about it, we generally talk about it as a percent, right? Um, so with simple linear regression, our R squared is simply a measure of how much of the variation in our dependent variable, our independent variable is explained, right? So a higher R squared is good. It means that this one variable explains a lot of the variation in variable y, right? Or so say we go back to the example where I was looking at marijuana usage and income. So we look at that one. Oops, I went too far. There we go. Our R squared is 0.01. So actually, no, that's birth weight and smoking. There we go. So 0.005. So the proportion of variation that I can explain in income using marijuana usage is only what? 0.005 or 0.5%. I'm probably not really getting very good predictions of why just using this number of days someone used marijuana. There's probably a lot of other variables that are explaining a lot more of the variation in income, right? Income depends on a lot more than just one thing. So when we only try to predict it using one thing, our predictions are going to be pretty bad. We're missing a lot of the variation. So now you're never going to like be calculating this necessarily by hand. I'll show you. Well, we could do that. I'll go through an example in Excel where I kind of prove this to you and we can reproduce an R squared. Um, but just to kind of show you another example, I also had this one where I had my dependent variable was salary and my independent variable, things are kind of hiding it, but it's publication rate. So this is a bunch of professors, their publication rate, so how many articles they're publishing per year, and how much that increased their salary, right? So it's kind of a weird one, or actually it was negative, but that's something that we'll tackle later, which is probably have a lot of other important omitted variables here. And I could compare different relationships. So, the publication rate looks like it has an R squared of 0.5. So it's explaining about half of the variation, 50% of the variation that exists in salary. While if I try to run a regression and predict salary with experience, that R squared is 0.1. I'm explaining a much smaller amount of the variation that exists in salary. So here, if I'm only using one variable, the publication rate is probably going to be a little bit more accurate in when I'm making predictions because it's explaining about 50% of the variation as opposed to about 10%. Okay. So here we would say the publication rate is a better predictor. So before we go to multiple linear regression, I wanted to show this to you in Excel. Okay. So we'll go back to our percent vaccinated example because we already have the regression output here. I can look at my R squared is about 0.04. So remember, and I'm going to rename this as oh, one. I'm going to copy and paste this data real quick, just to kind of keep separate. Call this reg2 example. All right, so zoom in so I can see what I'm doing. So I've got my X variable and my Y variable here. So what I said with the, let me see if I pull this up. So we should be able to calculate the R squared using these two formulas. So that's what I'm gonna kind of prove to you. So here we're gonna take predicted Y minus the average Y. Then we're gonna take the difference between Y and the average Y. Excuse me. And we're not only gonna take those differences, but if I'm recalling correctly, it's the, oops. There we go. It's those deviations squared. Right? So I need to then make sure when I'm doing this, and this is just so you have some labels. So I'm gonna, right. So what do I need? Well, I need to know what Y bar is, or the mean of my Y variable. So I'll take the average, enter. Right? Now, this is a kind of cheating, but it's more to give you a comprehensive look. So when we actually did estimate what that slope and intercept coefficient were, so I'm just going to go here. Where did we have them? So here was my slope coefficient. Here was my intercept coefficient. Okay. So one thing that I need here is, oh, what are my predicted Y values? I don't have a column for that yet. So I'm going to move this over just to give myself a little more room, because I need to be able to come up with the predicted Y values. How will I do that? Well, that's just going to be my intercept plus slope times whatever the X value is. Now here, when I copy this down, I want to make this prediction for every single observation. I want that X value to change, but my intercept and my slope values that I estimated, those aren't going to change at all, right? That's what I'm using to make my predictions. I'm then going to double click, does it for every observation. I'm then going to take the predicted Y value minus the mean of Y and then square it. When I copy this down, I want to update the prediction, but not the mean. So I'm going to freeze that cell reference. And then I'm going to do the same thing over here, except for I'm going to take the actual Y value, subtract the mean, square it. I don't want that mean reference to change, so I'm going to freeze it. Now I'm going to go down, double click. Now I've got it for every single observation. Right? So what I'll then do, we kind of think about my numerator and my denominator. So the numerator was adding up the sum of all those deviations of my prediction from the mean, and then the denominator is the sum of the actual deviation and the actual Y value. So here, I'm going to add up all of these deviations of my predictions from the mean. So Control Shift or Command Shift on the Mac, hit the down arrow, hit Enter, will send me back up to the top. My denominator was the sum of the actual deviations from the mean from the actual Y values. So I'm going to select that column of data, hit Enter. Now my R squared should be the ratio of these two. So 0.0, sure enough, 0.0407, even to be, I'm getting the exact same value. So you don't have to go through by hand and do this, similar to the other stuff I showed you, but it does kind of prove to you that these equations are working correctly. But ultimately, you can always just grab that R squared, the regression output. Okay. So the final thing we're going to talk about is we can do regression, but we can include multiple variables on our right-hand side. So I don't just have to have one independent variable, I can include several, right? So now my predictions for y will include the intercept, a slope coefficient associated with the first variable, slope coefficient associated with the second variable, et cetera, right? So you can kind of imagine, maybe a setup for this is maybe I want to predict crime rates using police force expenditures, but also the unemployment rate of the area, right? And we'll see why being able to include this additional variable of unemployment might dramatically change the results I get for that slope coefficient. So you think about this line of best fit, it's kind of hard to say. So before with just one variable, we could kind of do a 2D scatter plot and think about a line of best fit. Once you start having like multiple coefficients, well, if you do two, it's kind of like if you could like do a 3D scatter plot and draw a line that best fits that. Um, you know, it's kind of, gets crazy after you have more than two, right? Because now you're 4D, 5D. But essentially the process is the same. You've got an equation. You just want to minimize the sum of the squared errors, right? So here's my error term, the difference between the actual y and my predicted y. It's just now to get my predictions, I've got more moving parts. Well, now I can take a derivative of this function, the sum of my squared errors, in respect to each one of these slope coefficients. I'm now going to have n plus 1 because of the intercept, um, equations, n plus 1 unknowns. I can solve that, right? So the solution, I mean, the math is probably a little bit too complicated in terms of the prerequisites for this class, but Excel can do all this math behind the scenes for us, but the procedure is really the same as what we talked about with just one uh, independent variable. You take a derivative of this function in respect to all of these coefficients. You've then got a set of equations with the same number of unknowns. You can, through some complicated math, solve that. Right? So if you're interested, I put a link, goes to the steps a little bit more, interpret, but I don't expect you to go through this or be able to reproduce it. We're going to use Excel output in order to obtain these coefficient estimates, these slope coefficients. So the interpretation of our slopes, our slope coefficients, is going to be exactly the same as it was when we only had one variable on the right-hand side, but now we get to add in this additional term. So it's the expected change in y from a 1-unit change in x, holding all the other variables that we include in our regression constant. So you can imagine this is pretty powerful. Like if I just think about this crime example, well, if I didn't have the unemployment rate, this would be the effect of spending $1 more on my police force. But I know that areas that spend more money on their police force probably need to, right? So if I can control for the unemployment rate in the area, now the thought experiment is two areas with the exact same unemployment, but one of them spends an additional dollar on their police force. What's the predicted change in crime? We can calculate, so we can calculate the R squared. It's very can be almost identical to what we were doing when we had one variable. It's just that now remember, it's the percent of the variation that we're explaining in the dependent variable from our regression. And our regression now includes multiple dependent variables. So if we think about the sum of those squares residuals now, our predictions include all of our independent variables. So however many x variables we've included on the right-hand side. So here's kind of like the proportion of variation we can explain. We still have the total kind of variation that exists in the data. And then we can also think about this from a different standpoint, which is what can't we explain? And what we can explain is going to be the difference between the actual y values and our predictions, or our errors, right? Errors squared. So we've got some of the squared errors. This is what our independent variables can't explain. Some of the squared residuals, what we can, and then the total sum of squares is just the total variation that exists. So everything's basically the same. It's just now it's not how much variation does one variable explain, how much do all of our independent variables explain. Okay. So one thing you might be interested in, okay, maybe I have a relatively low R squared. So maybe it's like 0.1 or 0.15. So I'm not explaining a lot of the variation, but it doesn't necessarily mean that the variables that I'm using to make my predictions aren't important, right? Maybe my regression model is still, the variables I've included in it are good ones to use. Yes, hopefully I can go out and find more data so I can explain more of the variation and why, but maybe the ones I'm using are good as well. So I'm going to put these up here. I'm not going to make you do this by hand. I'll show you where these things exist in Excel, but we're going to have our mean our mean square roots of our regression. This is going to be the sum of our squared residuals divided by the number of independent variables that we're including. So you can kind of think about it here. This is going to be what I can explain, or what I can, sorry, I'm kind of slurring my words, what I can explain using my regression model, like using my predictions. However, if I just start throwing tons of variables, I can always increase my R squared, right? Even if I'm trying to predict income and I add someone's height, well, their height might, influence some of their behaviors. And so maybe that leads to different levels of income. So if I just start including more variables, I can always get a higher R squared, but I'm kind of cheating. If I just put like 1,000 variables in there, right? Some of them are going to stick, right? So kind of what this does is it like scales, okay, yeah, we're explaining this much of the variation, but we've included this many variables, right? We've included 1,000, right? So it's going to kind of scale that down. And then kind of the mean of our squared errors, this is going to be what we can explain, divided by kind of our total number of observations minus our number of independent variables minus 1. Once again, we're not really going to use these a lot because Excel does this work for us and it spits out our F statistic. And then it's just a matter of how do we use this F statistic to make decisions about whether or not our regression model was significant. So when we say is the regression model significant, I did a 2 variable example here. It would just get more complicated if you added 3 or 4 variables. But here I'm going to start out assuming that both of these coefficients associated with the 2 variables I included in my regression are equal to 0. So I used beta here. You might see that in regression models using beta instead of B. It's just the kind of the Greek notation. So I'm trying to kind of show you a little bit of both. And this is a small typo, so I'm glad I'm catching this. I think I just copy pasted and forgot to update it. So my alternative hypothesis is that one of these is not equal to 0. So something that I've included in this regression has some effect, right? Has some relationship with y that's something other than 0. And then, if we can find evidence that supports the alternative and goes against the null enough, we say, okay, I can reject that both of these coefficients are 0, or essentially what we're assuming is that the model explains nothing. So if we can reject that, we're saying our regression model explains a significant amount of the variation in y. Okay. So, if I'm thinking about an F statistic, it's going to be very similar to what we were doing with other distributions. Let me see here. I gotta flip this. There we go. So the F distribution has a longer right tail. It's not symmetrical. So it's going to look something like this. But ultimately, we're going to do hypothesis testing a very similar way. And just like the student T distributions, the F distributions are going to depend on some type of degrees of freedom, but we're not going to have to choose which one. Excel will do that for us. Dive into those topics more if this is a more complicated stats course. Excuse me. But it's still the same idea. I can find critical values that give me a desired alpha in the tail, right? And, I would calculate my F statistic. If it's in that rejection region, I can reject. Notice its p-value would be less than alpha. So all the same principles apply. It's just that we're using a different distribution. And the reason why, if we think about what we're doing, we're testing the model's significance. Well, I'm always going to know that R squared is always going to be positive, right? And at the very worst, it could ever be is 0. So I can never see negative R squared. I can never explain less than 0 of the percent of the variation in the y variable. So we always know that we're going to be looking at kind of the positive values, which is why our F statistic, our critical values are always going to be positive, right? We're looking at the right-hand side there. Okay. So kind of similar to our student T distributions, although it has 2 degrees of freedom instead of just 1, we're not going to kind of work with F tables, or I'm not going to make you do any of this. All we're going to need to know are those same rules that apply from previous hypothesis testing, which is we reject if the p-value is less than alpha, or if our F statistic, our test statistic, is greater than our critical value. Okay. So here's non-Excel output. I'll then show you what it looks like in Excel, but notice, okay, here's my F statistic. It even tells me my degrees of freedom here. So 44.23. probability that I see that F statistic or anything greater, or essentially it's telling me there the p-value. Right? So my p-value is basically 0. So I think I was trying to predict wages using IQ, age, and experience in this regression. So these three variables, right, this model that I'm trying to use to explain the variation that exists in wage, I would say, is significant at any conventional level, right? My model is statistically significant at any conventional level in terms of explaining the variation that exists in wages or making predictions for wages. Okay, so pretty high F statistic leads to a pretty low p-value. So any level of conventional significance, we can reject the null. Remember the null being that none of the variables have any effect. Okay. The next thing that we'll kind of work through, I'll relate this to the crime example, kind of jump the gun a little bit already. But let's say I run this regression and I find that when counties or cities spend more on their police force, that the slope coefficient's actually positive and that they see more crime. Well, that's probably because they were spending more money because other conditions were bad, but we're not controlling for those, right? So, if we include the unemployment rate, now the interpretation is one more dollar spent on my police force holding constant the unemployment rate of the area. Well, that's a lot more powerful of a statement. Maybe then the sign would actually flip. So as I add in more regressions, these slope coefficients can change because I'm now controlling for more things. I'm holding more things constant. Same kind of idea with smoking and birth weight. If you look at data, yes, the effect of smoking while pregnant is negative on birth weights. But, and I think I put positive here and it's negative, clearly. But even though I find it's negative, could it be positive? So if you look at the correlation of mothers who smoke while pregnant, it's also highly correlated with things like socioeconomic status, education level, like all these things that might also lead to changes in the birth weight. So if we don't control for those things, we might find a really strong negative effect here, when in fact, yeah, it's a negative effect, but not near as large. Right? So what is this going to look like? So correlation is not causation. So the problem, if we omit important variables, so this is where if I just use a simple linear regression instead of using multiple linear regression, I'm not controlling for these other things z, which might be causing both x and y to change. So maybe it isn't that x is causing y to change, but that some outside factor is causing both x and y to change. So, got an example here. So like, for example, if I looked at the correlation of autism and organic food sales, if I run this regression with this data, I'm going to find that there's a positive effect. I don't think that organic food sales are causing autism rates. It's likely an outside factor, which is driving both of these up. Maybe an increased focus on health in all areas. So people are buying more organic food, but they're also being more attentive to their children's health and diagnosing autism earlier. And so maybe there's this outside factor causing both of them. Also the old stupid cartoon I always like that said this. So the one I started the class off with some statistics, how to lie with statistics or something. And this was if you run a regression, you'll always find a positive slope coefficient between drowning deaths and ice cream sales. But right, drowning ice cream sales aren't causing drowning deaths. It's temperature, right? This other thing, Z, we're not factoring. So I used to think correlation implied causation. Then I took a statistics class. Now I don't. Sounds like the class helped. Well, maybe, right? Because, maybe it wasn't that taking the class helped me have this realization. Maybe it was that I was more likely to take the class because I was intelligent and it was my intelligence that led me to be able to figure this out. So kind of a stupid little example. Now, I won't dive into this because I'm not going to make you guys kind of work through all this, but basically you can prove that if you run a simple linear regression, just including one variable x, and you omit an important variable, another variable x2, that you're always going to find that your slope coefficient has the true effect, right? But also this bias, this additional component, right? So we're saying our estimate is going to be biased there, right? So I've got kind of this example to kind of run through what this looks like. So here I've got being an athlete and its predictions on your GPA. And then I say, okay, well, what if I include just one more variable, which is that person's SAT score? because, admissions departments may be a little bit more lax on student athletes than non-student athletes. And so maybe it's not that being an athlete causes you to have a lower GPA. Maybe it's that, athletes tend to have lower SAT scores coming in. Or, maybe the effect of being an athlete, if I could hold constant the person's intelligence level, maybe it teaches things like um, time management. So maybe it actually has a positive effect. Okay. So you can look at these results. And I've got this in Excel. So I'm just going to actually jump over to Excel in this omitted variable tab. And you can kind of see all these tables are what I just copied them into slides there. So we'll kind of reproduce them. So I've got GPA, SAT scores, and whether or not they're student athletes. So I'm going to go up here. First thing I'm going to do is run a regression where I'm looking at my Y variable is college GPA. My X variable is whether or not they're an athlete. So select that, Control Shift, Command Shift on a Mac. I've selected my labels, hit OK. Zoom in so I can see what I'm doing. So it looks like there's a negative effect, and the p-value is basically zero. So I can reject the null that there's no effect on GPAs for being a student athlete at very high levels, right? So e to the -9, remember, move that decimal 9 places to the left. This is basically a p-value of 0. So I can easily reject the null. So I found a pretty strong negative effect, but I then go back and say, well, look, I know that, admissions standards might be different, especially at these like major D1 universities. So I'm going to go back to my data analysis regression. And instead of just selecting athlete, I'm going to select two of these variables, right? SAT and if they're an athlete. So Command Shift to the Mac, Control Shift at BC, hit OK. Now when I get this regression output, I can see here that, okay, now the interpretation of that athlete, so the unit change is kind of weird here because it's just, are you an athlete? 1, 0 if you're not. So going from not being a student athlete to being a student athlete predicts that your GPA will be about 0.05 points lower, holding constant the person's SAT score. So we went from a scenario where it looked like being a student athlete actually decreased your GPA by 0.28 and was highly significant, to now it only reduces it by 0.05 once I hold constant the person's SAT score. And I can't even say that being a student athlete has any effect, right, at any of our conventional levels, because our p-value isn't going to be less than any of our alphas. Okay. So what's another thing we can do? So let's go up here. I don't just have to include two variables. I can include a bunch. So here for my X variables, I'm going to select everything I've got here, right? Except for this SAT squared. We're not going to do anything with that. So hit OK. Zoom in so we can see what I'm doing here. So now the interpretation of my student athlete variable, if I include all of these other variables, is holding constant the SAT score, this verbal math score, their high school rank, whether they were female, their kind of demographic controls, their total credit hours, their high school size. So two students where all those things are exactly the same, but one of them is a student athlete, they would actually expect that their GPA would be about 0.17 points higher. And it is now, once again, e to the -5th. So this p-value is basically 0. It's significant, but now the opposite direction, right? Now we can say there's a statistically significant positive effect from being a student athlete. So you can kind of see if you have important other variables that are important and you're omitting them from very simple regressions, these aren't very reliable coefficients, right? In fact, you can kind of see a lot of these are highly significant, right? We should have been including them. And you'll notice as we add in more variables, what's happening to our R squared. So originally, the proportion of variation we explained was 0.0 or 0.08 or 0.8%. So being whether or not you're a student athlete doesn't explain much of the variation in GPAs. SAT score, once we included that, our R squared should be, our R squared shot up a lot, right? This SAT variable looks like it's really good at explaining a lot of the variation in GPA, about what, 0.16, right? Because being a student athlete didn't explain much. Then if we include all of them, now we're up to about 0.3. So we're getting close to explaining a third of the variation that exists in GPA. There's likely a lot of other important omitted variables that we still don't have, but these results are a little bit more reliable than when we were just running a simple linear regression. Okay. Once again, the F statistic we talked about earlier, I can say here, is this model, is this a good statistically significant model explaining variation in GPAs? Well, the F statistic is huge. The p-value is basically 0, so yes, right? I can reject that this model explains no variation, right? And then even here, I could reject even just including SAT and athlete. Hell, even just including athlete, I can kind of reject. Okay. Okay, so let me think if there's anything else I want to say here before we go back. Slide. So I've got everything that I just did there, kind of, slightly different format, but this is the results that we saw from Excel. But we can see once you start including these important omitted variables, things can change quite a bit, right? Our coefficients can change signs, they can change whether or not they're significant or not.